Yes,
good?
I see your video and sound is okay.
And you should see my slides.
So the next talk, the last talk today, will be from Christian Marciniak, Marciniak, University, Innsbruck. Have I pronounced your name correctly?
Well, close enough.
Close enough. University of Innsbruck, yes.
Yep, all right. Well, thank you for having me. My name is Christian. I will be representing the trapped ion quantum information efforts we have in Innsbruck today. That's something that actually has quite a bit of history. It's quite a long history. Rainer Blatter started this in Innsbruck more than 20 years ago. I realize I'm the last thing between many of you, coffee break or a nap after a long day. But lucky for you, I will be giving just a very broad overview talk. I won't go into much detail on any of the things that I'll be talking about, but of course you're free to ask questions. And I do have backup slides with formulae if someone really wants them. So in the 20 years since Rainer started his group, it has grown to somewhat north of 50 people now. And consequently, we have a really broad spectrum of things that we do. Today, I would like to give you a brief introduction to quantum information processing with trapped ions, as I've been asked to do. And after that, I will tell you a little bit more about the group, the very many different teams and streams, if you will, that we have, and a bit of a flavor of the things that we do. I won't have an opportunity to touch even lightly on everything that we do. And this is, as I said, very much aimed to be an overview talk. And I will try to give you a flavor of a lot of things. Try, I say, because I'm obviously not an expert in all of them. And so I will be fairly brief. If there's time and interest at the end, I can talk a little bit more detail about some select projects, or if there are bachelor students in the audience, I highly encourage the less senior people to ask questions if they're interested in something. And with that, I'll like to dive right in. And I realize that some, or probably even most of you, aren't intimately familiar with trapped ions, or for that matter, quantum information processing. So here's a very simple illustration of our platform, what it looks like. We use linear Paul traps. So that's a type of ion trap with which we can find individually charged atoms or ions in an ultra-high vacuum chamber. And there are other types of traps, but we mostly use these ones where we have, let me get this thing up, where we have these 4 electrodes that are blade-shaped in this particular configuration, where we have an oscillating electric field on that leads to confinement in the radial direction, so in the 2 directions orthogonal to these. And then we also have these DC electrodes we call end caps that provide confinement in the axial direction. And then if we set the parameters, so the different voltages in a particular way, and we cool the ions, we can make them crystallize in strings, truly one-dimensional strings along the axis of the trap. And then we can take images of this, all of our interactions, including readout or optical. In this cartoon, you can see this box which says CCD, so that's a very expensive CCD camera. And as I said, we interact, manipulate, cool, read out, and do all the operations that we need. And we do this with light, and it's laser light. And the information for quantum information processing is stored in the electronic states of ions, and we can read them out using this camera. You can see here a real image of a chain of calcium-40 ions in one of our Paul traps, and each of these dots is an individual atom. The ions that we use, I already mentioned, are mostly calcium-40. So there's a little bit of atomic physics here, but that shan't be too daunting given the other talks today. Calcium-40 is an alkali ion, so it has a single unpaired electron that makes it in some respects similar to hydrogen. And we have ourselves an atomic qubit, so it's natural, not man-made like some others in the talks today, in fact. And by virtue of this natural occurrence, they're all exactly identical. And if you're familiar with such things from atomic physics, you can see the level scheme here, very simplified, but it's an archetypical form of alkali ions. Importantly, we have a strong dipole transition between these two levels here, which scatter a lot of light. We can use these for detection and cooling of the ions. And then we also have an electric quadrupole transition that's dipole forbidden, so it's very weak and therefore narrow. And we encode quantum information in these two levels. If the electron is in the lower level, in the ground state, it is available to scatter light on this transition. It's bright, and we call this down or 1. And if it's up here in the D state, it's not available to scatter light on this transition. It's dark, and we call that 0. And so detection is state dependent based on this difference in fluorescence. This used to be called, quantum jump detection by electron shelving. Nowadays, we just call it detection because it's commonplace. And what I've just described is an electronic degree of freedom, which we use to encode our qubit. You can do many other things, but that's what we do mostly. And it's determined by where the electron is energetically. This is combined in an ion trap with the harmonic oscillator that the trap itself presents, in which we confine the ions. This is a bosonic degree of freedom, quantum harmonic oscillator. And together they form a coupled system that we can jointly manipulate using laser-mediated interactions. At this level of abstraction is actually identical to, even superconducting qubits, where the harmonic oscillator is a cavity for microwave photons. But that's just as a side remark. The ions themselves are so far apart that you don't get native spin-spin interactions which we could use to couple them. But they have this shared potential. They sit in the same harmonic potential of the trap. So we can use a harmonic oscillator to afford us the capabilities of producing spin-spin interactions. And so if we shine light in on a transition that is resonant with the qubit just from the ground to the excited state, this is what we call a carrier. This is independent of whether there are other ions in the trap or not. And this we can use to produce single qubit operations. And if we detune our light and shine it in on so-called sidebands, which are resonant with a transition where the number of phonons, so the excitations in the harmonic oscillator, changes as well, we can use that to create entanglement. So in quantum information processing, this is often described as a bosonic bus that mediates spin-spin interactions. And these are all things that have been known for a very long time. For trapped ions, the first proposal to do such a thing was by Zirac and Zoller. Peter is also in Innsbruck. And then when you have these different operations, performing quantum algorithms, at least in the gate-based approach, just boils down to concatenating series of laser pulses. You can use these carrier pulses, which are resonant for arbitrary single qubit operations. And then you can use pulses on sidebands in some way or another to create 2 or more qubit gate operations. And that's indeed already sufficient for universal quantum computation. And then we can, for example, analyze the quantum state that we have created by performing a circuit or something, by performing tomography, where we perform repeated projective measurements. And these carrier pulses give us the freedom to rotate our bases to whichever we want. And so that's already sufficient for arbitrary single qubit bases. And we can use, for example, parity oscillations if that's something to witness entanglement, among very many other things. And here's a little graphic. I know it can be a little bit smack in the face because it's a lot of things at once, but it's a summary graph of the different types of operations, or some important types of operations that we can do. And I've grouped them into global and local, and then collective and addressed. So we can use laser light that goes through axially, hits all the ions at the same time, and have it resonant. Then each of the ions performs single qubit operations, just all the same, and they don't care that there's others. We can use detuned, for example, a Mohr-Sorensen entangling gate, to perform global entangling operations where this all-to-all connectivity that trapped ions have through this bosonic bus means that we can perform a G8Z or create a G8Z state with a single gate, for example. And then we also have the possibility of addressing. That means that we shine laser light only on subset of ions from the side with very high fidelity, and we can do arbitrary operations on arbitrary subsets of ions, either for single qubit or for entangling operations. And then we have, of course, quite a lot of different setups. The workhorse at the moment is the Action Compact Trapped Ion Quantum Computing Demonstrator. It's a long name, but it's something that looks a lot more like a computer than many other quantum computers, in the sense it sits in these standard 19-inch server racks. Connection to the outside is a LAN port and a power plug, and that's it. And it's a full-fledged quantum computer. We have spent quite a bit of work on the miniaturization, compacting, and automated tune-up and maintenance capabilities, because as we scale up to larger quantum registers, it makes no sense to keep doing things by hand. That's not how computers should run. And at some point, actually, if I do this by hand, I'm just fighting entropy. The system has drifted away before I even finished my first calibration routine. So I don't want to be spending too much time on crunching through numbers, but something that we're quite happy with is that we have, with all these automated tune-up and maintenance routines, a duty cycle of somewhat north of 80%, which I think is very good. And this compactness doesn't come at the cost of performance. Indeed, we currently hold the world record for the largest fully entangled state without error mitigation or post-selection. And this compactness makes it fairly hard to take intelligible pictures of the thing because it's very high fill factor and it's just a lot of aluminium plates. So a little bit of CAD. We have these two racks, and one is mostly the lasers, so we call it the optics rack, and then the others is the trap and a lot of electronics, so we call this the trap rack. It's not overly original. Right now, it's me and a PhD student, Vanya, working on it. And here's some of the more intelligible pictures. It was created as part of Action, which is one of the Horizon 2020 projects that recently finished. And the trap itself sits in a little drawer that is down here. Again, hard to take a picture, so more CAD. We can pull this drawer out. It sits in a magnetic shielding under normal operation, but of course, sometimes I have to get my hands in to adjust stuff. So we can pull this out. And down here we have, it sits on rails with active magnetic fields, vibration stabilization. And so we make away with the typical AMO lab, which has a several ton heavy optical table. And that works quite well. It's centered around a pine trap that we bought from AQT, which is a startup that came out of the University of Innsbruck. And that's about all that I want to say in this little crash course on trapped ion quantum information processing. Of course, you're happy to ask later, but I'd much rather move on and tell you about the group, which is quite large, and the very many people that are in it. And many there are. This is only a subset of the people at last year's group retreat in Obergurgl in Austria. This year's retreat is in the second week of August, so at which point I'll have a more up-to-date picture. Team is very international. We have people from 4 of the 5 continents and collaborators from all over the world. And the different projects that we have that are populated by these people, they work across very, or at least somewhat different fields. We have a number of teams working on quantum computation. I make a distinction between computation and simulation, although some people might say that's arbitrary. We also have people working in simulation with different crystal geometries. We have, for example, 2D ion crystals in Paul traps. We also have Rainer's first experiment and long year passion project in fundamental quantum optics with a single barium atom or ion. We have different trap geometries, a 2D trap. We have quantum networking, some hardcore precision metrology, and then Tracy Northup has their own group that is associated with us, and the startup AQT. And one of our PIs recently got a ERC START grant to form his own group in the quantum control of molecular ions. Right. I think you will agree that's quite a lot. And unsurprisingly, that means that we have a constant need for new people. We're always looking for good students and postdocs. And I appreciate that male students cannot leave the Ukraine right now, but you know, all terrible things shall pass, and we shall be looking for students and postdocs after this as well. Innsbruck doesn't just offer really cool science, it also has other features. You can see a picture that I took 3 weeks ago on a nice mountain trip. So I'm actually taking the picture. I'm not in the picture, but I was there, you can believe me. And this picture is taken up here, and this down there is where campus is. And this is where the university sits in the Inn Valley. It's very nice. So as I plow through some of our research pushes, maybe you will find something that seems a good fit to you, so you can consider joining up with us. Plus you have the nice mountains. And you can think about, you know, as if you are in the early career or in the early stages of your studies, maybe this is something you can look forward to be doing as you progress. The first thing that I want to talk about is stream-wise is the quantum computing and quantum error correction. That's something that's predominantly led by Thomas Mons. Some of you might know him. I have lots of shiny pictures and not a lot of formulae. Some prominent examples of the things that we do are topological qubits and quantum error correction, which we have a very nice paper down here, just now recently published in Nature, about the first fault-tolerant universal gate sets on 2 logical qubits. And then this is the question how we can make quantum computing robust against errors. We also look into the question of, once you do have a quantum computer that outperforms a classical computer, how would I possibly know and be able to tell whether it's working correctly? So that's quantum characterization, verification, and validation, where we also have some nice work on. And of course, we also do smaller projects in algorithms and applications with academia and industry. So yeah, 2 industry collaborations. One was in quantum finance, in portfolio value estimation, and this down here was in randomness and privacy amplification. So it's a cryptography application. Second push is, of course, there's no reason digital quantum computation should intrinsically be limited to computational units base 2. So that's something we heard of earlier today with photons. Harriet Watt University, Martin Ringbauer was actually there doing just that a few years ago. And then he joined us and is now bringing his expertise to trapped ions. He also recently secured a START grant, which we're very happy about. And one reason you shouldn't possibly limit yourself to base 2 is that nature is naturally higher dimensional, and Qudit, quantum information processing, so D again being the dimension, is something that Martin is leading. And a reason we should possibly do this in ions is that they naturally already encode more quantum system or quantum levels than just 2. So earlier I showed you where the upper level was just a line, but actually in calcium-40, for example, it's quite a few more lines. So in this particular isotope, you could be doing a Q-sept, I suppose, so 7 levels, 7 dimensions. We also already have some nice work on this. Martin recently published a universal gate set for qubits with qubit level control. And on the archive, we have single setting quantum state tomography. This is a way of doing tomography, let's say more resource efficient. This is a practical difference, whether of course the number of measurements you use doesn't go down. It's the number of settings goes down and the number of shots in that setting goes up. But for many experimental platforms, changing settings or changing bases is actually more expensive than doing more shots. So this leads to a dramatic speed up in the time that we need to perform tomography. And a second big push that we have is analog quantum simulation with spin chains, which is mostly led by Christian Roos and also Ben Lanyon. It's somewhat different flavor in how it's done to what I was just talking about. So I'll give you a very short detour to that. If you've been paying attention to the other talks, I guess this will ring familiar. But a big difference here is that we don't use gates, but a continuous time evolution that engineers an underlying dynamic that we want to study. And a very common model that we've already heard a lot about today is the Ising model. You can see down here, which is one of the statistical spin models. You typically ask a question like, what's the ground state of this, or what's the dynamics of this ground state, and you try to study that. And then we can map this to a linear chain of ions, even though the underlying dimension of the model could be, for example, two-dimensional. So this engineering also benefits us in the way that we can change model parameters that in nature are just fixed. You have something and that's it. So we can actually study a whole different class of problems, or even by changing some of the parameters, change the model itself. So by changing some parameters, we can go from this transverse field Ising model, which is very simple, to the more complicated flip-flop or XY class of Hamiltonians. And you might be surprised or flabbergasted even that a linear chain of ions can do 2D, 3D models. But maybe you know this thing here is called the Marciniak. It was a device that is made up of tanks of water and pumps and valves, and it was studied, used to study the economy of the United Kingdom before the dawn of digital computers. I would think you will agree that this doesn't look like the economy or the United Kingdom. So my point being that the physical appearance of something isn't always too important for what it can simulate. And then a typical experiment you would do in these sorts of simulators could look like this, where you prepare the ground state of the chain, and then you flip one, you create an excitation or a quench, what it's often called, and then you turn on this interacting Hamiltonian, and you study the dynamics of quasi-particles that exist in there. And in example projects, for example, is to me the very fascinating emergence of classical hydrodynamics in quantum magnets, or environmentally assisted quantum transport, or also the environmentally prohibited transport in long-range magnets. And you might be wondering why there's an image of enormous bees on this slide. And the reason is that the underlying statistics that describe the dynamics in the emergent hydrodynamics is governed by Levy flights, which also govern the flight paths or patterns of bees. And fun fact, also how hungry humans search for food. A somewhat different flavor of things that we do is combining quantum metrology, so the study of measurement, with quantum information processing. This will be familiar to some of you, maybe it's surprising to some others. That's something myself and Christian Roos are working on. The idea is that you can use concepts, control capabilities, or platforms that you have developed in quantum information processing and use them for metrological purposes. We've had a very nice project here together with Peter Zoller on optimal metrology, where we've coined this new paradigm of the programmable quantum sensor to enhance, in this particular implementation, optical clocks, but in principle, any sort of sensor that you can think of. And importantly, this is a descriptive proposal. So it's not the claim that it exists. It's, okay, give me what you have, I can tell you what you need to do, this sort of thing. And it's been using variational quantum algorithms to achieve this, although you're not limited to doing that. And then those that are experts in the field know that multi-copy, multi-parameter, or multi-copy, multi-parameter metrology is pretty popular right now. So we also have our hands in that particular pie. And then I mentioned already the barium experiment, which Rainer brought to Innsbruck more than 20 years ago. He is still working on this, and it's a departure from all the other experiments in the sense that it's not actually quantum information processing at all. It's hardcore quantum information, quantum optics, excuse me. And the general idea here is to study the interaction of a single quantum particle with its mirror image, which then can interfere and look at what effects that can have. And the things that you can use this for. For example, you could look at this from a metrological point of view, where you can suppress light scattering that can give you, for example, for position sensing, an increase in the imprecision. You could use this in computing, where again, if you suppress emission of light, that could hit a neighboring qubit and cause errors. You can study the motion of dipolar scatterers, so levitating nanoparticles. But something that I personally find also very fascinating is that we think of spontaneous emission as something that is just, it's kind of there. And we may have learned in lectures that it's the interaction with the vacuum modes, and you have to solve very difficult stochastic equations. But you can also, by interfering the image of a single scatterer with itself, just make it invisible. It forbids spontaneous emission in this, so you cannot scatter light of it. You can't see it. And all of this is made possible by placing it in the focal point of a hemispherical mirror. So you can capture actually half of all the light that it emits. And then there's this research push into quantum networks, quantum interfaces, and quantum communication, which is done by Tracy Northup in her own group and Ben Lenyon with us. And this formation of the quantum internet and how to do this. So there are several cavity QED experiments, quantum electrodynamics, that we have. There's 2, soon 3 nodes already here. And it's using optical cavities combined with ion traps. You can see some lenses here, and these are mirrors. They come in different shapes. For example, this is what we call big cavity because the mirrors are macroscopic, they're big. So there's light in this direction that you can capture and enhance from the ions. We also have fiber cavity, where this cavity is formed between the tips of 2 fibers that are very close together. And the form factor of the trap is also very different. So here, these 4 are the blade electrodes. We call this a wheel trap. And then Ben Lenyon also looks into a long distance communication. Ions typically don't have emission at the transmission window of silicon fiber. So one way to do long range transmission is to convert frequencies from what the ions have to what the fiber needs. And then to do this in a way that preserves quantum coherence. And in doing so, we've been able to create entanglement between 2 nodes separated by about 500 meters, 2 buildings on campus, which beat the previous records of just a few meters between traps in the same lab. And so we can store entanglement in the calcium qubit as a quantum memory. The general idea is here to interface matter nodes with traveling qubits or photons. All right, and that was, as I realized, a bit of a tour de force across what several research fields are and the work of very many people. There are a lot of names here. We have a lot of theory collaborators, some of which are here or people that you may know. If nothing else, I hope I gave you an impression of the breadth of research that is going on in Innsbruck and the idea that if you are interested in it and you have the opportunity, it's certainly enough to keep you and your friends busy for quite a while. Something that I'd like to mention right now as well is that maybe you do know, but maybe you don't, that Ukraine is eligible for EU funding as a medium to low income country, I think it's what it's called. And I'm already seeing Ukrainian institutions on a European Union calls on their website, so that's very good. But if you're not aware of this, this is certainly a resource that you can make use of. There's a lot of calls right now because the last funding round has just ended. And with that, I'm happy to take questions.
Thank you, Christian, for this very nice, bright overview talk. I see that we have questions now from the chat. And Nikolai Vitanov asks, how do you handle or reduce the crosstalk and how much is it?
Right. I don't have slides for this right now, but there is lots of data on this, also some of it published. Crosstalk in the addressed geometry is mainly limited through, right now at least, limited through the size of the beam. So you just have to focus the beam very tightly. We use large numerical aperture objectives to do this. Ours is 0.6 with the trap electrodes. It's limited to about 0.5. So we are around 800 nanometer waist size. And that gives us crosstalk in Rabi rate. So the quadratically more sensitive in the percent level. So, 1% worst case average is 0.2% in Rabi rate. So square that for intensity. And then there are certain fundamental limits. So even if you got rid of all the aberrations and that can cause stray light, you still get stuck with the fact that the spontaneous emission of the light from the ions is, in all of space. So it's totally possible that a photon that one qubit scatters or emits hits another one and causes an error. That's certainly a crosstalk flaw that you can't get around in that fashion, although there's this OMG architecture that's been recently proposed where you can get around that. Or you can use larger distances to quadratically reduce this between the ions. It comes at some cost. Or you can use like Honeywell or now Quantinuum multi-species crystals. But if you ask me, the OMG thing is a more sensible route.
Thank you. Then there are two questions about topological qubits. So from Vladimir Bezguba, can you say a few more words about your work on topological qubits? And from Nikolai Vitanov, do you consider topological qubits as the way to go for the scalable quantum computer?
Sure, I'll move to some slides about that. Yeah, so we use the 7 qubit Steen color code. You see a colorful picture of this here. So the 7 balls are physical qubits. The colored plaquettes and edges tell you something about how they're connected. This forms a single logical qubit. It has some nice properties. For example, that the entire Clifford group is transversal. If you're an expert in this, you will like this. So that includes the 2-qubit gate. The T gate is a bit more complicated. We use the concept of flag fault tolerance to perform fault tolerant operations. So fault tolerance means that if you have a physical error on one of the qubits, which is correctable, and you have entangling gates, this error can spread to more than one qubit, which isn't correctable. Fault tolerant requires that this doesn't happen. There's different paradigms of how you can manage that. A lot of them are very resource costly, either in terms of number of gates or in terms of number of ancillas. We have been using this relatively novel idea of flag fault tolerance, where you have a non-fault tolerant encoding state. So this circuit here makes logical 0, but it's non-fault tolerant because this error here can spread to 2 qubits. But then you have a second verification step where you map the occurrence of dangerous errors to the state of an ancilla. And then you post-select on whether the flag is up or not. And if the flag is not up, it's been there was no uncorrectable fault. And if it's up, you disregard this. And here's some data from this Nature paper where you can see that the amount of uncorrectable errors is gone down dramatically, and even the amount of errors, no errors, has gone up. And then the second question was whether I think this is the way forward. I think yes. All efforts in quantum error correction thus far that have shown much promise have been on topological protection of quantum information, whether it's error correcting codes or the may or may not exist of Majorana modes. I don't see right now how else large scale and indefinite quantum computation should work. I hope this answers your question. Otherwise, ask again.
Okay, I see no reaction. Thank you, probably. One more question from the chat from Olga. How you protect your experimental system, Rex, in the beginning of the talk from external noise? Probably she didn't believe in your damping, yeah?
Yeah, so there are a couple of different avenues that we've pursued. One is engineering. So the racks themselves are not very stable. You probably looked at this. There is earthquake resistant variants, but that doesn't mean they don't shake. They're a large tower. So vibration is a big concern. Now, luckily, the industrialization of quantum technologies is in full swing. So there is a lot of companies that now produce let's say industry grade in their resilience, but scientific grade in their performance products that are also rack mountable. You may have heard, for example, of the OptiClock project, which is now a rack-based transportable atomic clock with above 10 to the -16 in Allen variance. So that's one thing, that you can get components that are resilient to such noise sources like vibration. And of course, they need to fulfill EU criteria for shielding and so on. The next thing is the things that we do need to make ourselves. We make small and modular, small so that vibration amplitudes are reduced. We use, for example, for light switching, double path configurations or cat's eye, which are insensitive to motion to the first order. And then the trap itself, well, it sits in a mu metal magnetic shield. It's 60,000 euros of very expensive alloy that shields against magnetic fields. We do have some cold atom people in the lab next door. So that means we actually have large switching magnetic fields that we also do feed forward on and feed back with sensors. And then we have this active vibration isolation stage of the trap module, which is the only thing really sensitive to vibration. And that works fairly well. We don't have a quantitative measure of the stability at the ion location because there's no reflectors inside the ion trap to do, for example, Doppler velocimetry or something, or some Michelson interferometer. We have published noise figures for the vibration on the breadboard if you want to look up in that paper. And then we have this rack-mounted 1 Hertz diode laser system, 1 Hertz line width diode laser system from Toptica, which was one of the research outcomes of action. And that is also on a vibrational isolation stage. So there's a bit of engineering involved in making this be not terrible. And it really boils down to you really knowing what the thickness of the isolation polymer should be and all these sorts of things. But it's manageable.
So it's really serious stuff. Okay, I do not see the raised hand. Maybe then a few last questions, naive questions from me. I was wondering actually how you can see with light, how you can see single atoms.
Yeah, so on this S2P transition, it's at 397 nanometers. So that's where cameras are still sensitive. You don't even need fancy phosphorus or something on that. And then we have a 0.5 numerical aperture lens. So we can capture a fair bit of flat light.
I mean, it's visual light, right? It's
well, it's near UV, yeah.
Yeah, UV. Okay.
Yeah.
But the size of the atom is much smaller. I mean this.
Yeah, sure. I mean, we don't see the atom. We see the airy fringe of a point source, or the airy pattern of a point source. That's true.
The pattern of what?
The airy pattern of a point source. So the emitter is point-like from an imaging perspective.
Okay.
Yeah. So if we had no aberrations at all, you would see nice airy fringes. That's actually terrible. We don't want airy fringes because they give us crosstalk. So it's actually advantageous to not fully illuminate the imaging objective.
Okay, and this potential along the chain, how it's formed?
There's just a DC voltage.
DC.
So along the chain, we have just a DC voltage applied to both electrodes. So it squeezes like this. It forms a harmonic oscillator in that direction. The radial direction is more complicated. So we have an oscillating electric quadrupole field.
Yeah, radial direction, it is like mass analyzer, quadrupole mass analyzer, I guess, yeah?
Well,
Similar.
Quadrupole mass analyzers are Paul traps most of the time.
But still, DC, I don't understand. It is mainly these potentials, how it is formed along the chain?
It's electrostatic.
Electrostatic, okay.
Yeah.
Okay.
So, I mean, Poisson's equation tells us that it can't be static in all three directions. So 2 of them are dynamic and 1 is static.
Okay, and finally, you also manage that it is like in approximation of harmonic oscillations, yeah, harmonic oscillator. But actually, I learned, for example, for superconducting qubits, that it is especially important that it is nonlinear, to have its anharmonic and to have different levels. So how can you distinguish these different levels? How many levels? I mean, excited states. This is oscillations.
Well, it's unbounded, and the number of modes of this harmonic oscillator is 3 times the number of atoms. So in the radial direction, we have 2n. They are distinct in frequency, but as you increase the number of atoms in the radial direction, these frequencies, the number of modes increases faster than the bandwidth, so we get mode crowding. It's actually a major problem in ion traps that these modes come close together.
Okay, thank you very much. I see Andrei.
Yes, I just want to use the chance to ask one more naive question. Christian, I just wondered, when you consider another physical system, nitrogen vacations in diamonds, so then another degree of freedoms plays a role. So this is related to atomic nucleus. Yeah.
Sure.
And I just wonder that in this atomic research, people do not say about this degree of freedom, or I missed something maybe. It doesn't play a role at all, or maybe you have some access to this, or to, for example, to spin off nuclei of atomic nuclei or to something like this.
Calcium-40 doesn't have nuclear spin. So
it doesn't have nuclear spin, yeah?
In this particular isotope, there's no nuclear spin. Calcium-43 has nuclear spin, and there's reasons to do one or the other. We have an optical qubit, so we encode it between the S and D level. If you have an isotope with nuclear spin, you can do ground state qubit by Raman transitions. There is an entire zoo of different species and isotopes with very many different encodings. So yes, we do have access to the nuclear spin via the hyperfine interaction. And then you could use either direct microwave radiation or use Raman transitions to change it.
And is there in this case some interaction between electrons and this degree of freedom, like nuclear spin?
Well, yes, because this interaction is what forms the hyperfine splitting, right? So if you, I would say it like this, in most cases, the underlying nuclear spin will change if you do a transition, right? There are certain transitions where it doesn't, but that's most of them will.
Okay,
so, yes.
Thank you very much. Yeah, thank you. Now it's clear. Thank you very much.
Thank you, Christian, then. And I also thank to all lecturers. I'm sorry for ignoring the coffee breaks on the last session, yeah, but I hope that people now can stay, especially taking into account advantage of online workshop. And I hope that tomorrow we will continue with the same success. Thank you very much.
Bye.